Alright, back to figure 7.6. I'm going to talk about a couple other things. We've already talked about the conditions at rest. We're now going to talk about the conditions with exercise. But before that, I just want to summarize a couple things here. So basically, we're looking at pressures of oxygen and CO2 in 4 different places. So we're looking at the pressures in the alveoli. Okay, we've talked about what those are, and those are here. That's those. And then we talk about the pressures in the arteries. Okay, and those are here and here. You can see those are the same. And we've talked about the pressures in the veins. Okay, and those are here and here. And again, you can see those are the same. And then lastly, we talked about the partial pressures in the cell, and these were the numbers that I gave you. Okay, so on the workbook, there's a lot of questions about where is the PO2 or the pCO2 higher, in the venous blood versus the alveoli, in the arterial blood versus the cell, etc. Basically, all I'm asking you is where's the pressure higher? And if you know which direction the gases move, you know where the pressures must be higher. Okay, so for instance, if I were to ask where is the PO2 higher in the venous blood or in the alveoli, PO2, you know that it must be higher in the alveoli because you know that the oxygen is moving from the alveoli into the blood. Okay, and so there must be a gradient such that the oxygen coming in has a lower PO2 than the oxygen in the alveoli. Oops, that's not right. Okay. And that's the case, and that's why oxygen moves into the blood, because we have a gradient of P1, which is 105, P2, which is 40, 105 minus 40 is 65, so we have a PO2 gradient of 65 moving oxygen out of the alveoli into the blood. Okay? So on those questions, those are the different areas that I'll ask about. Okay. So now let's talk about what happens during exercise. Okay, so during exercise, what we see is that the numbers in the alveoli are the same. Okay, so these numbers do not change during exercise. Okay? And because the blood equilibrates with what's in the alveoli, so what's in the arteries ends up being equivalent to what was in the alveoli, then these numbers, oh, that's 105. Then these numbers are not going to change with exercise. They're going to be the same. Okay? So basically, what's in the alveoli and what's on the arterial side is the same during rest with exercise. Okay? The body is always going to equilibrate back to 105 and 40, and therefore that's what's always going to end up coming into the cells. Now, what does change during exercise is what's going on in the cell, right? Because during exercise, our muscle cells are working, okay? And when our muscle cells are working, they're using oxygen and they're producing CO2. So what we see during exercise is the cells have lower oxygen than they had at rest because they're using it, and higher CO2 than they had at rest because the cells are producing more. Okay. So the resting values for PO2 were 40 and pCO2 was 46. Okay, that's rest. and I'm talking about the values in the cell. Okay. So during exercise, PO2 drops, PCO2 rises. Okay. And so PO2 during exercise can drop. I'm just going to give you a number. It's actually a real number. PO2 is going to drop, and it's going to drop more with higher levels or higher intensities of exercise, because as you do more work and you need more ATP, you're going to use more oxygen. So we see that the PO2 in the muscle cells can drop as low as 18 with exercise. Okay. So if we drop the PO2 in the muscle cell to 18, okay, PO2 coming into the cell is still 105, so P1 is still 105, but P2, instead of being 40, P2 is 18. You can see that we will now have a pressure gradient between the cells and that capillary blood of 87 instead of 65, which means there's a stronger gradient moving oxygen, which means oxygen is going to move out of the blood into the cell faster, and therefore we're going to end up with less oxygen left in the blood when it enters the veins. And remember that this capillary blood equilibrates with the cell, so during heavy exercise we're going to end up with a PO2 as low as 18 in our venous blood. Okay? And therefore the PO2 coming into the lungs is also going to be lower. It's going to be 18. Okay, so it's much lower than it was at rest. So this setup, this also sets up a bigger gradient in the alveoli. Okay, so this PO2 is still 105. That doesn't change. But instead of 105 minus 40 here, we have 105 minus 18 between the blood and the alveoli. So now we have a pressure gradient of 87. Okay, the PO2 in this blood is much lower, which means that more oxygen is going to have to drive into the blood to replace the oxygen that was used in the cells. Again, it's going to equilibrate with what's in the alveoli, so it's still going to equilibrate at 105, but much more oxygen is going to have to leave the alveoli to get the blood up to 105, because it came in lower. It came in at 18 instead of 40. And that bigger gradient is also serving to, let's see, where was that? The bigger gradient is also serving to increase the rate that the oxygen moves. So this gradient is higher for oxygen during exercise. Okay, which is good because that's what allows the oxygen to move faster during exercise. Okay, so we also see the same thing with CO2. Let's see, so much writing everywhere. So let's look at CO2. So again, what's going on in the alveoli is still the same as it was at rest. It's still 40, and therefore the PCO2 of the blood coming into the cell is still 40. But what we see going on in the cell, normally at rest we have a CO2 of 46. But because the cell is producing more CO2 during exercise, it's going to rise. And I don't have any real numbers for this, but it doesn't rise as much as oxygen, because remember that the diffusion coefficient of CO2 is higher, so we don't need as big of a pressure gradient. So let's just say that PCO2 during exercise goes from 46 to 48. Okay? So in the cell we have a PCO2 of 48. We still have 40 in this blood coming in, So now we have a gradient of 8. 48 minus 40 is 8, instead of a gradient of 6, which is what we had with rest. So now we have a bigger gradient. That's going to drive more CO2 out of the cell, and so the PCO2 in the venous blood is going to be equivalent to what it was in the alveoli. So we're going to see a PCO2 in this example of 48 coming out of the cells, and therefore the PCO2 of the blood going into the lungs is also going to be higher. It's going to be 48, which then again sets up a bigger pressure gradient at the alveoli than we had at rest, and that's going to drive CO2 out faster, okay, during exercise than what we had at rest, which is necessary. Okay. So during exercise, the pressure gradient at the alveoli and in the cells of both oxygen and CO2 is greater, and this is the gas diffusion rate. So the gas diffusion rate is going to be faster for both oxygen and CO2 at exercise than it was at rest, which makes a lot of sense because during exercise you're doing more work, you're using more ATP, you're using more oxygen, we have to replace more oxygen, you're producing more CO2, we have to get rid of more CO2. In order to do this, we have to diffuse the gases faster because you're using them, you're producing them faster, the blood is moving faster, so everything fits together nicely the way it should. Okay. So I recommend using the workbook and going through all of the different questions that I've asked, where I've asked you pretty much every combination of comparing, venous to alveoli, alveoli to artery, artery to cells, cells to veins, and basically answering in which area is the PO2 or PCO2 higher. Okay? So make sure you have a good grasp on that because there's a number of questions that can come from this picture and general concept.